Good morning.
Okay, so back, could you just give Victor a few seconds to read this one? Okay, so that.
Good morning, ladies and gentlemen. My name is Šťavina. I'm going to present our solution to problem number 17, Popsicle chain reaction. We are to slightly bend Popsicle sticks to join them in so-called cobra loop. When such chain has one of its end release, it rapidly dislodges wave front travels through the chain. We are to investigate this phenomenon. The chain must be weaved in a manner as you can see in the picture. When one of these sticks is released, the wave travels through the chain. It is important to note this angle theta, which will be important nextly in our presentation. Also, when we pull the green stick, it is not equivalent to the red stick, and with the pulling of the green stick, the cobra phenomenon occurs, as can be seen here in the video. While when we put on the red stick, it just bounces off the ground and explodes in this manner. We will be concentrating on the green stick phenomenon. This one occurs because when the green stick is released, the cobra rises as the sticks get expelled downwards, as you can see in the diagram here. The sticks, as they get expelled downwards, they impart a recoil onto the end of the cobra, rising it. Another forces that are acting on the end of the cobra is the elasticity of the cobra as we bend it, and also there is the gravitational pull onto the cobra. We will be in the first part of our presentation concentrating on the height of the cobra, which is defined in the place where the sticks are not part of the weave anymore. In the beginning of the phenomenon, as the time increases, we see cobra rising, and it gradually enters the steady state. We can see that this indeed happens, and nothing else. As the cobra rises in this measurement of a 7-meter long cobra, we can see that there is observable height limit. In the steady state, the height of the cobra may look something like this, and we can see this from the stable equilibrium of the forces we have shown before. There is also sometimes an oscillatory movement, which is the result of the dynamical equilibrium of these forces. Let us move on to the theoretical account, which in the beginning we will be focusing on the elastic potential energy of the sticks. This depends on the dimensions of the stick and the radius of curvature of the stick in the weave. In first approximation, we will demand that the potential energy will be equal to the elastic potential energy. The potential energy in the gravitational field will be equal to elastic potential energy, arriving at this formula. We can, from this, estimate the height, but we need to note that this expression will be extremely sensitive to the quantity r, the radius of curvature. With this, we need to determine a method. We need to define a method of determining the radius of curvature, which we will do geometrically using the GeoGebra, obtaining the radius of curvature accurately. Also, in the formula I have shown you before, there is the Young's modulus, and we will not be using the table values, but rather we will measure it. With this simple formula, it can be defined and measured for one stick, and for this particular stick it is obtained this value, and in the cobra we measure several sticks to obtain the average Young's modulus. So, with this formula, when we compare it with the height that it tends to reach in steady state, we get a clear overestimate. This should make sense because there will be indeed more energies in play, such as are the potential energies and rotational energies imparted on the sticks when we leave the cobra. From this, indeed, we can arrive at the correct model for the height, which involves also the rotations of the sticks and such, but we will see that, and we see that it correlates with our measurements. Here you can see five measurements of the same cobra correlated with it, but it is extremely problematic to obtain all the data such as RP rotations, so we will see a better theoretical model. First, we will check the literature, and we will see that they indeed can determine the cobra height based on such expression, where this is the curvature of the cobra, but this would require solving third order or ODE. So we will get inspired by this because they obtain this from forces. So we will get inspired and we will study the forces as well. Firstly, there is the recoil forces, the elastic and the gravitational forces, as we mentioned in the beginning. We will focus now on the recoil force, which will have direction opposite to the sticks leaving the cobra and can be defined as this, where the m is mass of one popsicle, Vt is the terminal popsicle's velocity, and frequency is the frequency of departures, f. And then there will be another force, which will be acting perpendicular on the end of the cobra, and it is the elastic force, which is dependent on the Young's modulus, the displacement of the free end, and the dimensions of the sticks. With this, finally, we will focus on the gravitational force, which is this rather daunting formula, but we will see that there enters the length of the cobra and the linear mass density from which this complicated term comes from. It is from studying the geometry of the setup. We will demand the balance of forces and arrive at such formula for the height. When we compare this with our experiments, this formula is dependent on the geometry of the cobra through the angle theta I mentioned in the beginning. So when we look at the dependence on the angle of theta, we arrive at a good correlation for the different thetas. Then we can change also the width of the cobra, which also affects the formula I have displayed, and we arrive at correlation. Next thing we be concentrating on is the wave velocity. Indeed, the cobra in the steady states travels at a steady velocity. The theory for this is analyzed in the literature, arriving at this formula. This formula is gives us the idea how the velocity scales with different parameters. We need to note that this function is a dimensionless factor that depends on the geometry of the whole cobra. We will estimate it to scale as cosine. Well, so from the experiment, we will be able to determine the velocity, as you can see it indeed is the steady state velocity, and we will see that it scales as we predict. And for the specific sticks they used in this article, we arrive at psi equal to 3.95, as well as they do in the article. So, moving on to our own sticks, we estimated the psi to be to scale as cosine of theta. So we can see that, so why is it that we estimated is as such is that with small theta, that there will be a less dense cobra. So, with one expelled stick, the traveled distance is greater for this cobra, and therefore the velocity should scale with cosine. Indeed, when we plug in cosine, we get such a trend here, correlating with what we thought. Next, what we will be investigating is the effective length of the cobra, of the sticks woven into the cobra, which also affects the velocity, and we can see that indeed the velocity scales as 1 over L squared, as you can see in the picture here. So, to summarize, what we did was we presented the cobra as it as we should create it. We presented qualitative theory based on potential energies, and then we corrected it with the forces, as you can see here. Then we are investigating the effect of changing angle and width on the height of the cobra, and moreover we presented theory taken from an article for the angle and length as it affects the wave, the velocity of wave propagating through the cobra. I would like to thank you for your attention.
2 minutes time for questions from the audience.
Therefore, the could you please open file number 45, and while opening, could answer the question, what's the nature of
45?
45, yes. What's the wave that travels along the cobra? What is the wave?
The wave is...
The wave of what? What's the wave? Elastic, maybe, or...
Well, it is, this elastic deformation that
Okay,
travels.
I got it. On this frame, I see that there are different sticks, so I'm sure that the modulus of right and left and right and left pitches are the same.
These sticks are precisely the same. The only thing that was changed was the density.
If the Young modulus is the same. Yes
Well,
or no?
for these sticks, yes.
I got it. So, now please. So you use loss of literature in your mathematical model. Can you show? Are you sure that all basic equations that are used in the series are the same? For example, potential energy deformation, you use it. Are you sure that in all papers that you use, this equation was the same? For potential energy deformation for the cobra?
No.
Yes or no?
No.
I got it, thank you. So, what's the most important parameters of the surface in your opinion? The surface. The surface, like this. What's the main important parameters of the surface?
There is this parameter called second moment of the surface that affects this phenomenon. That's where we are.
Friction may be elastic.
Well, we were assuming that it is the friction is
I will discuss it later. Finally, can you observe the phenomenon with all the parameters of the cobra? So, are there some boundary conditions for maybe some geometry?
Yes, of course. There is.
And now slide number 7, please. I'm sure that elastic force has the correct direction on the frame. Yes or no?
Sorry, time's up. You gotta postpone that.
Well, it all
discussion.
depends
Sorry.
to the cobra.
Could you please proceed to preparing the opposition?
Okay, please start your position.
So, dear colleagues, my name is Ivan Polonik. I'm a member of the Russian team, and I'm happy to present you our position of problem number 17 for cycle chain reaction. Let's go to the main results of this report. There was an energy information model for killing this phenomenon. It was told that potential energy of the formation of the stick goes into kinetic energy that you have forward and rotation component, and the potential energy of gravity. I agree with it, but not at all. Of course, there are some energy loads, for example, friction between the sticks, friction between the floor, air resistance, and also oscillation of the cobra. That can be very important because of human factor on control, and if it is in control, cobra can oscillate in the perpendicular direction of its motion. After it was also explanation based of force balance. I agree with it. It's okay in my opinion. After it was a split of front investigation, but it was a model that mostly based on the papers. So it's not so strong point of the support. After it was told about the head of the cobra, it also was mostly cited of the papers and just comparing a few operations from the papers to one big and comparing it with the experiment. So it isn't so good in my opinion. Also it was based how the geometry of the cobra can change the phenomenon. It was investigation for angle between the sticks, this one, and how the lens changed. But I'm not sure that really in experiments with different lens, Young modulus and for example point duration were the same because it wasn't proved. So the main strong points of the review were qualitative explanation of stick rising, of why the height of the cobra is constant. It was because of the force balance. They were all forces acting on the cobra. It was investigation, not full, but it was primitive investigation for height and velocity of the cobra. And for example, length of the sticks was changed. If you talk about the not so strong points for the report, for example, it was that roll of the surface wasn't investigated at all. In my opinion, roll of the surface is one of the main important parameters that can affect the height of the cobra. We'll discuss it on the we'll talk about it on the discussion. It was not so mostly theory was put from the papers. That isn't so good because if you talk, for example, it's because this problem was played previous year on student phenomenon. If we see the equation he had in beginning. Lots of them were in Greece team paper publicated after the tournament. It's named Kasaros. You can check it if you want. And human factor experiment wasn't good effect. So if that was a task fulfillment, what can we see? We were asked to create the cobra. Yes, it was done. The motion of my front, yes, it was observed. But after the investigation, it was not full. For example, it was mostly checking the papers, and it wasn't some novelty and something from the reporter. So now I'm ready to go to discussion. And we must solve the problem.
Okay, so firstly I would like to tell something about my own contribution. The theory from the forces was derived not from the articles, but by us.
Yes, I agree with the theory of the force, but the equation parts, they were mostly
that was not really a problem as you are.
So I guess this is not the question we should discuss in the
Okay.
answer. So let's now talk about the, first of all, we begin with things the most clear part, the mechanism of energy change. So we have some cobra like this, yeah?
Yeah.
And so we can speak from this end away, and what's happening?
Well, firstly, what happens is that cobra rises, then it reaches steady state, and then it terminates.
And so what is that energy, so how the energy of the system can transfer? So first of all, we have only potential energy of the formation,
Well,
and what it goes into.
This energy starts to transfer to the potential elastic energy. It starts to transfer to the energy of, well, the kinetic energy as the cobra rises, and also there is this potential energy of well, the other sticks. Yeah, gravitational potential.
But
The balance was written also
in my
on
opinion,
the slides.
I suppose see the sticks that this one sticks that are going to play, they rotate. They rotate.
Yes, of course.
So
There are
it's
also
also component of energy that
Yes.
we could take into account.
yes, and it was also in the slides.
Yes. And the one thing that we didn't check, is energy losses of the system. So I didn't see in your report checking of low energy conservation energy. You didn't check if the energy is conserved, but you use it. So there,
Yes,
because there are also energy losses that can change a resistance process.
Well, we were assuming that these were small.
So you didn't check it anyway. So you can prove it. Can you prove it? Can you prove that these losses are very small or no?
We were assuming this. We were not
So
investigating this
no,
assumption.
Just assumption. Okay. So now let's go. So at this moment we've so this moment of discussion we understood that energy law of energy conservation was written not enough in full case, and it wasn't checked that
Okay, but it produced results. So we believe that this was not. Okay, so I will say that it did produce results, and we were mainly focusing on the theory that was derived from the forces, not from this.
So now I think the most important part of the problem is the role of the surface.
Okay.
So we didn't check the surface at all, yeah?
What we were considering with the surface is that the friction between the surface and the cobra is enough for the cobra not to move.
So in your opinion, only friction is important to the surface?
Yes.
So now let's have some mind experiment. Just we have cobra, yeah?
Yeah.
Let's look from the back. And now just imagine that we turn it back. So it's vertical now. It's like this. So this is like cobra.
Yeah.
And we release this angle. What will happen? So we have done surface on both ways.
So there will be a recoil from the expelled sticks onto the cobra.
So it's a stable position of the cobra. And what will happen? How will it move?
Well, as the sticks dislodge in this way, there will be force from recoil imparted.
Can you just imagine how can a wavefront look like?
That is truly a complicated phenomenon, and I can't say
Okay,
precise. But maybe.
Let's continue having our mind experiment. So in this case, it's like our paper, so it's look from the bottom of our and we release this end. Of course, for system, it's there are no change go in this direction or in this direction because gravity directs like this, so it doesn't affect. So in this case, it's obvious that some wavefront will go in this direction and some in this direction.
Of course,
Yes,
it does not happen in our case because
Yes, and if you have the surface, the second front doesn't appear. But if you change the surface, second front of the wavefront in this direction, it can appear. For example, you have
okay, but this is not part of the phenomenon.
I should all be the same. So if we take, for example, the table and this floor, these are absolutely different parameters of the cobra
I say that if we build the cobra here,
yes,
and that it would dislodge in the same way as if we put it on the table.
but why? So,
Because the normal forces would be still the same.
let's go to the food and continue. So you agree that if we have cobra like this, it will go in two directions like this, yeah? You agree with it?
Okay, yeah.
Yes, but now see, we have surface. It is easy to deformate like this cover, and it's cobra-rising. In my opinion, it's obvious that force with which these sticks will act the surface will be so cut that a small deformation.
Of course, if this surface is susceptible to deformation, then it obviously would change the phenomenon.
Yes.
But we were not dealing with this because that is not part of our investigation. What we were investigating is the height of the cobra and the way it travels. Yeah, but we were not encouraged to investigate surfaces that are susceptible to deformation. That would completely change the
All
task.
surface can have
The small deformations would not affect the phenomenon rapidly.
and how to understand the deformation are small. So which is the maximum deformation with which considered small? So what is the maximum volume of deformation? You can say that it's neglectable small.
We were not investigating this, and really, it was not important. I can't stress this more because with the surfaces we put the cobras on, they were not susceptible to deformations, and really.
Okay, so
If
I don't
disagree
with you that the surface is not important, but now let's discuss the boundary conditions, for example, for length and the shape of the sticks. So we have the sticks like it, and so this has some length, and you say that not with all lengths one can be observed. So what are the boundary conditions? What are the conditions in which this cover made of these sticks can rise?
Okay, there is some breaking threshold for these.
So one limit is breaking.
Yes.
I agree with it.
And the other limit is that there need to be stored enough energy, so when it is released, it is able to rise.
So
the compressor there is a limit imposed by gravity.
So that in the formation such as one is deformated, it should have more energy than in just right position. Yeah? So that the potential energy should be. So
the potential energy must be enough to rise the cobra.
So it is some maximum value or no? Will this give maximum value or minimum? So we have gravity and breathing. Which of them will be maximum for the length, and which will be minimum?
Wait, let me think through. Well, the diagram in which the cobra will exist will look.
Yes, I agree with that.
Something like this. And so.
But the question is, which of these limits is mixed maximum? And so, is gravity minimize the length, or is the breaking limit can minimize the length? What will minimize it?
Okay, so
which line is for gravity and which is for breaking?
This one only for gravity.
So what minimize the length? What minimize? So
when we minimize,
we have a question like this, yeah?
Okay, sorry to interrupt you there. There's no more time for any additional remarks. Will you please go summarize the discussion?
During the discussion with water, we've talked about first of all about the energy transfer in the system, that potential energy of information goes into kinetic energy in rotation and forward. We move to the copper. I agree with it. Also, but yeah, we think that it's some agreement between serial agreement, but not all coins have really good agreement. For example, there are also really big errors in Young's model's measurements. So air friction, for example, air friction could be important, and just including in the errors of Young's model measurements. So without proof, we can so no proof, no truth, we can believe that air friction is really small. After we argued about the role of the surface, in my opinion, it's the main point of this problem, and but Potter didn't agree. But in my opinion, it is. And after talk about the boundary conditions for the length of the spring. Thank you for your attention.
Okay, thank you. It's time for questions from the community.
To the reporter, do you believe that the popsicle will rise without the ground, if it wasn't pushing off the ground?
Well, the phenomenon would be completely different, and most probably would not
So would the amplitude of the wave
rise
actually increase?
per se.
Would the amplitude of the wave actually increase? Yes or no?
There would be a wave, but and it would move in a way, but
Right, to the Polonik.
In my opinion, if you don't have like turn back, yes.
Right, like let's say
In
you
this case, amplitude will decrease because it will have to go into two directions, and so it will be smaller, about in 2 times.
Right, also, why does the wave actually reach a steady state? Why doesn't it keep increasing? What's the primary reason?
because there will occur that the forces I described will balance.
Right.
In my opinion, it's because of our system is not plastic wave, it's outer wave, and while throwing sticks away, the system gets extra energy while the deformation energy potential, and it helps us rise higher.
So, to the reporter, one of the core assumptions in your theory is that the frequency, the number of sticks being expelled from the wave is constant, and therefore the velocity only depends on the angle or the length A to return. So can you explain why you believe the frequency, the number of sticks ejected, is constant?
Because it is an empirical observation, because and it should make sense because the cobra is the same everywhere, and as the sticks dislodge, they always dislodge in the same way. Therefore, the frequency of departure is always the same.
So in your beam theory deriving the elastic potential, what beam theory did you use? You used Euler's or Chen?
For the forces, the Euler elastic.
Okay, so what assumptions did you make?
The assumptions that were made was that the density of the cobra, the line density of the cobra is approximately the same. Of course, that it is continuously elastic medium, and that was really.
Okay, thank you, I understand. So what do you believe is the efficiency of the wave, conversion from elastic to velocity or gravitation? What's the efficiency? Just a rough number, efficiency. What % of energy is transferred?
I can't estimate it.
Like that,
It could be derived from
I
the
think it's
formula.
so hard to say without experimental data, so
It
I'm not
could
sure
be
about
simply
that.
derived from the formulas I showed for the energy, but I don't have the precise
Okay.
numbers.
What do you think would happen if I actually doubled the thickness of popsicle stick? What if I tape two of them together? What would happen?
Okay,
Well,
I'm afraid there will be no more time for an answer, so for that, and I would ask the viewing team to go Okay, please start the review.
Okay, so my name is Xiong from Canada, and today I'll be reviewing Popsicle stick reaction. So the problem statement goes as follows, and there are several tasks that I believe need to be addressed within this problem. The first is construct a well-controlled experiment to vary well parameters. It's necessary to be very precise in measuring the amplitude and also velocity of the wave. It's important to analyze the energy transfer or the efficiency, as well as to construct a theoretical model that actually predicts the amplitude and velocity of wave. And finally, the reporter should be able to experimentally verify the theory by varying the angle, material, and also the stick geometry. So for summary of the report, they began with a theoretical analysis. They started with the qualitative explanation of the wave formation, followed by using beam theory, using Euler-Bernoulli to account for the energy transfer, and also they found the amplitude they predicted the amplitude as well as the velocity. For their experimental confirmation, they used beam theory to account for the energy transfer. They also made several velocity and amplitude measurements. So several merits for the reporter. They had a very thorough qualitative explanation of the wave formation, as well as clear diagrams and visuals in order to help visualize the data for different angles. However, I believe that the theoretical model was very limited, as well as understanding of the phenomenon itself, as well, especially the importance of the normal force. They didn't state their assumptions of beam theory, and they didn't account for any dissipated forces, which are actually very significant in this phenomenon, as friction is what holds the wave together, and shearing forces are actually very significant. And there was very limited contribution. So in the later half of the presentation, literature was primarily used in making their theoretical. And also, there's very strong lack of experimental control. We don't know how they measure amplitude. We don't know how they measure parallax, and this is actually very significant for this problem. Now, for the opponent, there were effective general observations of the different sections into the theory. There were good analysis into theoretical strengths and weaknesses, especially dissipated forces, and also the experimental strengths and weaknesses. So for the opponent, they rightly brought up the efficiency of energy transfer and consideration of dissipated forces, though I would like to see at least an order of magnitude on what the efficiency actually is. There was efficient discussion of a qualitative explanation to bring up misconceptions. However, there's a lack of focus on a clarification of the theoretical model, as well as a system of the force balance, exactly how they were able to calculate everything, as well as a lack of discussion of the experimental setup, which I believe is very significant for this problem. Now, I'll just go into the discussion between the opponent and reporter. The first point was the efficiency and also dissipated forces. The opponent stated that there are non-negligible energy losses due to dissipated forces, while the reporter's response is that it is valid to assume that energy losses are small. However, and I agree with the opponent that energy losses, dissipated forces, are not negligible, and they should be quantified by carrying out an empirical fit for the efficiency of the energy transfer. But the second point is that the deformation of the surface is not negligible, while the reporter states that the role of the surface is irrelevant. I disagree with both the opponent and the reporter. The normal force is actually incredibly significant for the formation of the wave. Without pressing on the ground, the cobra wave wouldn't actually be lifted off the ground. And let's say if we were to drop the wave and release it, we'd have the same phenomenon as if we released the one stick where the popsicles would go directly off the ground. And in fact, in the very end of the chain, we observed that the wave would actually rotate in the very end section. This is incredibly significant in understanding this phenomenon. And finally, the opponent raised that there are breaking limits to gravitational and stick plastic deformations, and the reporter agrees with the point. And I believe this case is actually correct, and breaking limits do exist to observe the phenomenon. So for general assumptions, I believe the assumptions on beam theory should clearly be stated. The efficiency due to energy losses and dissipated forces should definitely be quantified in this experiment. And finally, the experimental procedure should be further investigated. There has to be analysis on parallax and measurement technique on amplitude and velocity. Thank you.
Thank you. Permit time for concluding remarks by the reporter.
I would like to firstly thank the opponent and the reviewer for their remarks. So I would like to just end this thing we started in the discussion, and that is when we have diagram for the sticks, where here is the length of the sticks and here is the width of the stick, then the breaking threshold is here, and here is the limit set by gravity. Then it was said in the review that the energy losses in the systems are not significant. We disagree with this because we are dealing with relatively small velocities, and therefore the energy losses are not that significant. Also, for the review, they stated that we said the ground is irrelevant for the phenomenon, but that is not true. I stated that indeed the force from the ground is important because from the force analysis we get two equations, in one of which indeed there is the reaction force which balances out in this component, and then we get the height from the other one because there is elasticity that affects the height. Finally, there was pointed the lack of own contribution, which we disagree strongly with, because the theory through the forces was developed indeed by us, and with this I would like to thank you. Okay, thank you.
And 5 minutes, 5 questions. If you don't mind, I'd like to go ahead. To the reporter, can you please bring up the force diagram on page number 20, slide number 29 again? So there's time for another question to any of the other teams in between if you want to. Opponent, review it. Otherwise, we'll wait for slide number 29. Okay, so we have a question for the opponent while waiting for slide number 29. Yes.
The opponent, so you said it about this dissipativeness of the dissipative forces, and you mentioned the air friction. What other friction you could mention?
It's air friction.
Or the balance. So you put first air friction or another friction should be.
My opinion is that air friction is the most important because
air friction.
because the cobra is its area is very high, and also about 2 meters per second is enough to.
So without air friction, we can't reach this saturated state. You mean that without air friction, the cobra can't reach this saturated state?
No, I mean that air friction just should be taken into account.
Okay.
Because without it, it can't preserve.
Did you allow a comment by the reviewer?
No.
Okay. My question on that slide would be, where does this force act on, and how does it evolve in time?
Okay, so these forces,
Yeah.
when in the steady state, they are not evolving with time.
What do they act on?
They are acting on the end of the cobra.
Okay, so what mass is inserted for calculating the gravity? Only the mass of the very last stick.
There is the mass of the part of the cobra that is risen from the ground.
Okay. Yes. I mean, does anybody else have a question first? Because we should answer this. Okay.
Reporter, you mentioned the frequency of departures.
Yes.
Yeah? It's this one. This is the independent parameter which you input, which you need to input in your theory.
Yes.
Or it depends.
Yes, it was something that was measured, and then
The frequency of this release.
Yes.
So does it affect to the velocity of this wave? Does it affect?
Yes, it has. Well, the velocity of the wave propagating through, no, it has no effect on that.
No. So if the frequency of departures is 0,
Well, so we don't have a clear relation for this. For the velocity of the wave as it propagates.
and according to your picture of the forces.
And it is related to the expression psi with that cosine of theta, but this.
Okay, sorry to interrupt you there. We
don't
shouldn't be the
have
same
a precise relation.
Okay. Question for the reviewer, if there's no other questions? Okay. You claimed that the efficiency of the wave should have been investigated, right? And you, in the previous presentation, you also mentioned that you would have liked to have a number for that. Could you give us a number for the efficiency?
So the efficiency for the gravitational is around 5%. We found that actually, when we take into account velocity as well as angular, it's closer around 40 to 60%.
Okay. No more questions? Okay, then I guess we'll proceed to grading.